Hello everyone, I'm Professor Sever, and today we're going to investigate a particular limit, namely the limit as x goes to 0 of sine x times sine 1 over x. And what we'll use is the Squeeze Theorem to evaluate this limit. So let's get started. Okay, so let's see what we need for this problem. So here's our knowledge base. Here are the four primary things we're going to need to evaluate this limit. We need to know the Squeeze theorem, which says if we have three functions, h, f, and g, such f is bounded by h and g on some interval I containing c, which means f is between h and g. H is the lower function, g is the upper function, and we've done squeeze before. You can see my video on that. And all this happens on some interval, except possibly at c itself, and we'll see most of the time f won't be continuous there at c, and therefore we want this inequality for all other values on the open interval. In fact, when we do this, as I've said before, the f, the one in the middle, this is the problem that you're working on. Okay, we'll need to know a simple fact about absolute values. If the absolute value of a is less than or equal to b, here b, of course, is positive or non-negative at least, then a is between negative b and b. We'll use that. We need to know sine is bounded by -1 and 1, which equivalently would be the same as saying the absolute value of sine of theta less than or equal to 1. In fact, you're seeing a slight application of this number 2 right here as well. Of course, here we have the biconditional. And the limit of the absolute value of sine x as x goes to 0 is 0. That's a simple limit, but we'll need that as well. Okay, so let's go ahead and use these facts in some order to evaluate our problem. And this is the problem at hand. We have the limit as x goes to 0 of this product, and we know this piece goes to 0, of course. Sine of 0 is 0. This piece is undefined, so it's indeterminate at that low level of analysis. We have 0 times something that's undefined. We don't know what that is, so we need to figure it out. All right, so let's start to apply the Squeeze theorem, and the artful part of the Squeeze theorem is searching for these functions that are above and below the target. And the target is, of course, the problem at hand, and that's the function that you're looking for. That's the f. All right, so let's look at this and see what we can. All right, so let's consider the absolute value of our f, which is the absolute value of our product. And I guess I could have added this, another simple fact about the absolute values. The absolute value of the product is the product of the absolute values. So this times on the inside comes to times on the outside of the absolute value. All right, now using our second fact, this is the angle theta in here. So this portion is less than or equal to 1. So this product then is less than or equal to, if I recopy this, left-hand factor. And if I replace this piece with something that's greater than it, namely 1, then this new product is bigger than or equal to the original. That should be straightforward because this is less than or equal to this. Okay, so let's recopy and see what we have just so it's clear. So we've shown then the original problem in absolute value is less than or equal to the absolute value of sine x. And now this is our second little piece here. So this is the b, and the a is inside the absolute value here. So we can now remove this absolute value in this inequality to get that the sine of x times the sine of 1 over x is less than or equal to the absolute value of sine x, but it's also greater than or equal to minus the absolute value So now, let's look at it carefully. This is the f, problem at hand. This is our upper function g, and this whole function there, that's my h of x. So see, we have h of x is less than or equal to f of x less than or equal to g of x, well, for all x excluding 0. So here the interval's all numbers other than 0. So now let's consider these two limits. All right, so the limit as x goes to 0 of the h, it's minus sine x. We'll move the negative side. And from our fact here, we said that we know that this is 0, and that is. We're just using that previously established fact. I have videos working on that. It's also usually in most of the textbooks. Also, let's look at the limit as x goes to 0 of g of x, which, by the way, is this right here, but let's just keep going. And this is the self-same limit that we just looked at. This is, now here's the key for any squeeze problem. These are the same number, L. Without that, then the squeeze wouldn't work. All right, so think about it. This limit's going to 0, which we just showed. This limit's going to 0, which we just showed. Now, this function is trapped between them. So what's the only number between 0 and 0? Well, 0. So it gets pinched or squeezed right to 0. So that's kind of the heart of the squeeze. So by the squeeze theorem, this is the final conclusion, the limit as x goes to 0 of sine of x times the sine of 1 over x, and that completes our proof of this limit via the squeeze theorem. Now let's look at the graphs. I have the graphs here. So here in red, this is the one, of course you can see it, it has a dampened compression. So there's a compression problem here. We're looking at the red graph. So, and it does look like it's dampening down to 0. The green graph here, see it here, this is the h. So h of x is equal to negative of the absolute value of sine x. And the blue graph here, that's the g. So the g of x is the absolute value of the sine x. And that should make sense because, look, this is the positive part of sine. I'm looking at the g. Well, what does the absolute value do? It flips up the negative portion. So that flips this part up. So this is our upper function g. The one in green is our lower function h. And you can see our target function is trapped squarely between them. It can touch, as it does infinitely many times. But since the limit of the blue graph and the green graph, which is h, go to 0, it forces or squeezes the limit of the red graph to go through the same place. And I've just zoomed in here. That's a visual. So this is on Desmos. This is just a visual representation of our three functions. And here, just as the same bit, if I zoomed in, I guess I could do it on the iPad like that, but I just zoomed in and showed the graph. Now, this is not a straight line, but if you zoom in pretty tight, then this has such a small curvature, it looks straight. This is just zoomed in even more to kind of show you what's happening with that limit close by 0. So once again, application of the squeeze theorem on a problem that's, you don't see this kind of problem every day. Usually you see something like x squared times sine 1 over x, but this is a little bit more interesting. And I'm Professor Sever. I hope that you enjoyed this video, and I'll see you next time.